Pluto is a remote and perplexing, more modest planet that was once a piece of our sun-fueled system's planetary gathering. However, later surprising announcements by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding discovery. They suggested that this cool world is on a potential influence course with Neptune. But how could this work out, and what might be the repercussions of such a giant event? Are we seeing a fascinating cosmic peculiarity, or is there something else to this coming limitless struggle? Join us as we investigate the possible results of a Pluto-Neptune impact. Pluto, a former planet that was renamed as a dwarf planet in part due to its astonishing orbit, remains a subject of interest and investigation in the cosmic community. According to recent figures by leading scientists, Pluto's orbit is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a likely dangerous collision between these two planets that could present a critical risk to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our nearby planetary gathering. It requires an amazing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't yet finished one full revolution. But the interest doesn't stop there. Pluto's orbit is marked by its exceptionally elliptical shape, wandering astonishingly from the almost round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, determined at 17 degrees to the ecliptic plane. The manner in which Pluto follows is significantly more extreme compared to other planets. This inclination and elongated nature add layers of complexity to its orbital design. One of the most intriguing aspects of Pluto's orbit is its intersection point with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we might expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The examination of Pluto's orbit began not long after its discovery. Initially, astronomers attempted to understand its unusual path in contrast to planets whose orbits lie somewhat near the ecliptic plane. Pluto's orbit stood apart with its steep inclination and stretched shape. The mystery deepened with the confirmation that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricate design of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how the orbits of Neptune and the Sun's gravity all interact in a complicated way. The terms libration and resonance, along with the VSK oscillation, are part of this puzzle, as indicated by astrophysicists. What's keeping all planets in their orbits is a libration. In the specific context of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it's arranged at least 90 degrees away from Neptune. This spatial division is critical in keeping their orbits from colliding. Resonance, libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated entirely above their orbital plane, providing an additional layer of protection from potential impacts. Another significant part of this condition is the VSK oscillation, named after three researchers, von Zippel, Kappas, and LV, who studied how objects move in space. It describes how three celestial objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VSK oscillation helps us understand why its orbit around the Sun is so unusual. Despite its seemingly turbulent path, Pluto's orbit remains stable for an extraordinarily long time, like billions of years. This means Pluto's venture around the Sun has a kind of order to it, even if it seems unpredictable at first. Predicting limitless events, especially when they involve violent orbits like Pluto's, presents critical challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a powerful means to understand and predict the future path of celestial bodies, they also highlight the limitations of our predictive abilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or deviation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the turbulent nature of celestial orbits like Pluto's reminds us of the constantly evolving and dynamic nature of the universe. While we have made significant steps in understanding space, the case of Pluto serves as a reminder that our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can create far-reaching effects on the stability and behavior of various bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential impact between Pluto and Neptune, despite all these intricate forces trying to prevent such an event from happening? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers an interesting perspective on the mysteries of our nearby planetary system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's interest in the unexplored realms of space. Tyson's position on Pluto's renaming is grounded in the ever-growing knowledge of our solar system. He sees the renaming not as a demotion, but rather as a significant adjustment in alignment with our developing understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of continuous learning and transformation. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these questions, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planetary system. His work stresses that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another respected physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often tumultuous forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with visionary concepts, making him an important voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to predict and understand potential astronomical events. He sees the interactions between celestial bodies as an important area of study, not just for academic interest but for practical implications. The potential collision between Pluto and Neptune, for instance, isn't just a theoretical situation but a reflection of the dynamic and often violent nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His perspective highlights the significance of being prepared for the unexpected in space. Kaku suggests that the more we understand the forces at play, the better prepared we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's viewpoints converge on the idea that space is a domain of boundless discovery, and that our current understanding, while significant, is still limited. Their emphasis on the need for ongoing exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now, but also anticipating how they may change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for effective scientific inquiry, advanced technology, and a willingness to revise our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational forces acting upon them. Therefore, a direct impact between Pluto and Neptune is extremely unlikely. However, the complexities and potential perturbations in orbital dynamics still mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may pose. While the possibility of a Pluto-Neptune collision is largely theoretical and considered unlikely with current understanding, it highlights the importance of continuous research and observation in space science. Advances in technology, including more advanced telescopes and virtual simulations, will help astronomers refine their models and predictions, ensuring that we stay abreast of the dynamic and ever-changing nature of our nearby planetary system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for ongoing investigation and a flexible understanding of our universe. The potential impact scenario, while highlighting the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast yet still unclear domains in our understanding of space. Through continued research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe. Pluto continues to captivate scientists and space enthusiasts alike with its distant, mysterious nature. While its status as a dwarf planet has long been debated, its orbit and peculiar characteristics keep researchers engaged. Recent developments have also placed Pluto in the spotlight once again, with the possibility of a gravitational interaction between Pluto and Neptune becoming the focus of attention in the space community. With Tyson and Kaku bringing this topic to the forefront, the discussion surrounding a potential Pluto-Neptune collision is bound to spark further curiosity and research. The investigation into these enigmatic celestial bodies holds promises of unveiling new insights into the mechanics of our solar system. As we peer deeper into space, the dynamic and unpredictable nature of our cosmic neighborhood only emphasizes the need for vigilance and ongoing exploration. While the potential interaction between Pluto and Neptune remains a topic of scientific intrigue, it is important to consider the broader context of space exploration and the methodologies used to study celestial bodies like Pluto. The discovery of potential risks, such as a possible Pluto-Neptune collision, serves as a stark reminder of the vast complexity and unpredictability inherent in the universe. It highlights the intricate mechanics at play within our solar system, where even the most seemingly stable orbits may harbor hidden uncertainties. This idea calls attention to the sophisticated tools and techniques employed by astronomers and physicists to understand the movement of celestial bodies. One significant tool used in such studies is numerical simulations, which allows scientists to predict and model the behavior of planets and dwarf planets over extended periods. By inputting known parameters such as the mass, speed, and distance of celestial objects, these simulations can project potential future movements and assess the stability of orbits like Pluto's. Such models often rely on powerful computers and advanced algorithms to handle the immense data and complex calculations required. This technique is especially useful when studying objects with unusual orbits, like Pluto, whose path around the Sun is so distinct from the other planets in the solar system. Additionally, the role of gravitational interactions between celestial bodies cannot be overstated. As mentioned, Pluto's orbit crosses Neptune's, and the gravitational pull between these two bodies could, in theory, lead to unpredictable outcomes over extremely long timescales. However, thanks to the resonance between Pluto and Neptune, their orbits remain locked in a stable relationship. This gravitational resonance ensures that even when Pluto comes close to Neptune's orbit, they never collide. The physics behind this resonance is fascinating, as it shows how the subtle forces of gravity can synchronize the movements of two distant bodies, preventing catastrophic events like a collision. At the same time, there are still questions about how other factors in the solar system might influence Pluto's orbit. For example, the presence of other planets, such as Jupiter, Saturn, and Uranus, could potentially perturb the delicate balance that keeps Pluto and Neptune in their stable orbits. These massive planets exert their own gravitational forces, which could cause small shifts in Pluto's trajectory. While these shifts are typically minor over millions or billions of years, they could accumulate and result in more noticeable changes. This is why astronomers continue to monitor Pluto's orbit carefully, looking for signs of any deviation that could indicate a future disruption. Beyond gravitational forces, the influence of the Sun itself also plays a crucial role in shaping the orbits of objects in the outer solar system. The Sun's gravity dominates the movement of all planets and dwarf planets, including Pluto. However, because Pluto is located so far from the Sun, the Sun's gravitational pull on Pluto is much weaker than on the inner planets. This means that Pluto's orbit is more susceptible to external influences. For example, the Sun's varying energy output over time, such as during solar cycles, might impact the behavior of objects in the Kuiper Belt, where Pluto resides. These subtle changes could affect the long-term stability of Pluto's orbit. Another key consideration in the study of Pluto is its environment. The dwarf planet resides in the Kuiper Belt, a region of space that is populated with a vast number of small icy bodies and dwarf planets. The Kuiper Belt is a relatively unexplored frontier, and many of the objects in this region remain poorly understood. As astronomers continue to gather more data from space missions such as NASA's New Horizons, which conducted a flyby of Pluto in 2015, we are beginning to gain more insight into this distant realm. New Horizons provided unprecedented close-up images of Pluto and its moons, revealing a complex world of icy mountains, vast plains, and mysterious atmospheric features. This data has opened the door to new questions about the formation and evolution of the outer solar system and how objects like Pluto interact with their surroundings. As scientists continue to refine their understanding of Pluto and its relationship with Neptune, one must also acknowledge the broader implications for space exploration and the potential for future discoveries. The study of distant objects like Pluto helps us gain a better understanding of the solar system's history, as well as the forces that shape planetary bodies. Moreover, these discoveries contribute to our ability to predict the future movements of celestial bodies, which could have practical applications for space missions and the future of human space exploration. With ongoing advancements in technology, our capacity to monitor and study the outer reaches of the solar system is expanding, opening new frontiers for both scientific inquiry and space exploration. In conclusion, the possibility of a Pluto-Neptune collision may seem unlikely, given the current understanding of their orbits and the stabilizing effects of gravitational resonance. However, it remains an intriguing subject for study, raising important questions about the complexity of our solar system. The work of scientists like Neil deGrasse Tyson and Michio Kaku serves to inspire further investigation into the forces that govern the behavior of distant celestial bodies. By continuing to observe, analyze, and model the movements of these objects, astronomers hope to unlock more secrets about the dynamics of space and the potential risks and opportunities that lie ahead in the exploration of our cosmic neighborhood.